Welcome to a presentation on truth tables by Dominic Corona. For similar videos on discrete mathematics, be sure to visit www.knowatom.com. We'll begin with an overview of logical operations. First, let's take a look at the AND function, also known as logical conjunction. This operation is denoted by an upside-down capital V, and is pronounced P and Q, with P and Q being Boolean values. AND evaluates to true only when both P and Q are true, otherwise it is false. The next is OR, also known as logical disjunction. This is denoted by a capital V, and is pronounced P or Q. The OR operation evaluates to true if either P or Q, or both, are true. Otherwise, it evaluates to false. Now let's look at the implies operator, also known as logical implication. This is denoted by a right-pointing arrow, and is pronounced P implies Q. This is true if Q is true, or if P is false. This means that P may be true only if Q is also true, and so it evaluates to false only if P is true, but Q is false. The equals operator, also known as logical equality, is much as you'd expect. It is denoted by an equal sign, and is pronounced P equals Q. As you can imagine, this is true when P and Q have the same truth value, either both true or both false. Finally, the exclusive OR operation, also known as exclusive disjunction. Denoted by a plus sign inside a circle, this operation is pronounced P exclusive OR Q. Exclusive OR evaluates to true when one or the other, but not both, of the Boolean values are true. This is a good overview of some of the most common logical operations, but there are others as well. Now, let's take a look at how to organize truth tables. Every Boolean variable or operation in your truth table has two possible values, true or false, sometimes denoted T or F, and sometimes denoted 1 or 0. As the number of variables increases, so does the number of rows in your table. More variables means a bigger table. Rows increase by a factor of 2 to the n being the number of variables you're using. So 2 variables need 4 rows, 3 variables need 8 rows, and so on. The number of rows is not increased by operations or negations. While P and Q are unique variables and count towards n, the total number of variables, not P does not. Neither does a statement like P and Q or P implies Q. Let's take a look at an example of truth table organization. Here we see a simple truth table with a single variable, P. The number of rows is 2 to the first power, or 2. The first possible value of P is true. The second possible value is false. The truth table is now complete. If we introduce a second variable, the number of rows increases to 4. Adding a third variable, we increase the number of rows to 2 to the third, or 8. A complete truth table needs to contain every possible combination of true and false for all its variables. While the order you do this in does not matter, it is important to have a method for filling out tables in order to make sure you do not miss any combinations. Here is one such method. First, make half of your first variable's rows true. In this case, half of 8 is 4, so we have 4 rows with T's in them. Then fill in the rest of the column with F's. Next, fill half of each half's rows with T's for the next variable. Finally, fill it up with F's. Every other is then filled with T's, and the remainder filled with F's. Notice that we alternated every 4, then every 2, then every 1. This pattern holds for any number of rows. So if you had 16 rows, you would alternate every 8, then every 4, then every 2, then every other, and so on. Here we have added not P to our truth table. Notice that this has not increased the number of rows in the table, as not P is not a unique variable. The not P column is filled in with the opposites of the P column, so 4 falses followed by 4 trues. This is because the negation of an expression is simply the opposite of it. Not P is denoted here by a squiggly line, instead of a sideways L like we saw previously. Either way is valid, and the squiggly line is often easier to type. Of course, without an application, truth tables serve no purpose. Luckily, there are a number of useful applications for truth tables. Let's take a look at some of the most important ones. Truth tables can be used to determine the truth value of an expression for any given combination of true and false variables. For example, we can look at what not P implies Q or P and Q evaluates to for any combination of P and Q. Here's a truth table for the expression. Each part is covered by the table. P implies Q, its negation, P and Q, and finally the expression itself. It is not necessary to have these extra columns, but it is very helpful, particularly for beginners, in ensuring you don't make any mistakes. Begin by filling in the true values and false values for P and Q. Next, fill in the first expression. P implies Q. Recall that P implies Q is only false when P is true and Q is false, which exists only in row 2. For the other combinations, it is true. Simply change each true to false and vice versa to construct the negation of this. P and Q is easy as well. They are only both true for the first row, and so P and Q is only true in the first row as well. Finally, fill in the table for the expression. If either portion of the expression is true, so is the expression itself, as they are joined by the OR function. So it is true in the first 2 rows and false in the second 2. Another application of truth tables is working backwards. This means if we are given certain truth values, such as a true statement and the fact that P is true, we can discover the truth value of the other variables. Note that this isn't always possible, and sometimes there are multiple solutions, but it's worth trying. Here we see the same truth table as we just worked with. We have been told that P is true and that the final expression is true, so we can fill in the column. Of course, building the whole truth table is one way to answer the question, but it is often much quicker to only work with one particular row. We don't need to finish the table, we just need to solve this row. Q is the variable in question, so now let's see if we can determine what it is. If the expression is true, one of its parts must be true. Let's first look at P and Q being true. P and Q is true. Q must also be true. However, there is another solution. Not P implies Q may also be true. If this is the case, then P implies Q must be false. Since P implies Q is only false when P is true and Q is false, Q must be false. So we've determined that if P is true and the statement is true, Q may either be true or false. In some cases, this method can be used to determine a specific value of Q, and in other cases, it may be discovered that it is a false statement. There are situations where if the statement is true, P cannot be true and vice versa, and this method can be used to prove that. Perhaps the most important use for truth tables is determining logical equivalence. For example, you may be asked, is P implies Q logically equivalent to not P or Q? To answer this, we can construct a truth table for both. Again, begin by filling in the truth values of P and Q. Next, complete the not P column. Now we can fill in the P implies Q column. Recall this is only false in one situation. Finally, fill in not P or Q. The truth table is complete. If you notice, the values in the first row are both the same, and the second, the third, and the fourth. This means that these two expressions are logically equivalent. They have the same truth value for any combination of true and false variables. It is useful to know that two statements are logically equivalent, partly because they can then be used interchangeably. You could use logical equivalence to simplify a complex expression. Another application of truth tables to logical equivalence is fast proof by contradiction. Proof by contradiction is a proof strategy where in order to prove something is true, we assume it is false. Then we show that it is actually impossible for it to be false, thus proving it is in fact true. We'll do that with truth tables for the logical equivalence question above. Let's assume that P implies Q and not P or Q are not logically equivalent. This means that one is true while the other is false. There are two possibilities to consider here. The first is true while the second is false, and vice versa. Of course, if not P and Q is false, then both not P and Q are false as well. And since not P is false, P is true. Since P is true and Q is false, P implies Q cannot be true. It must be false. We have disproven this first possibility. If P implies Q is false, recall that this means P must be true and Q must be false. This means that not P must be false. However, since not P and Q are both false, not P or Q must be false and cannot be true. We have disproven the second possibility. Therefore, we have proven that P implies Q and not P or Q are logically equivalent. In this situation, using this proof method doesn't seem any faster than building a complete truth table. However, for much more complex expressions with many more variables, it is often faster to examine logical equivalence in this way, as opposed to building the whole table. I hope you've enjoyed this presentation on truth tables. And remember, for more videos on discrete mathematics, visit www.noatom.com.